All right, everyone. Thank you all for coming. This is the wonderful world of designing a USB stack using modern C++. I'm Madeline Schneider. Before we get started, if anyone would like to follow along, this is a QR code to the slide deck. It is also posted in the Discord in case anyone can't access the QR code. So, yeah. Okay, a little bit about myself. I am currently a student at San Jose State University, finishing up my undergrad as a computer engineering major. I do a lot of open source work. The HAL logo you see is actually one of the logos of the projects that I work on. I have interned for the past 2 summers at Cisco, specifically Cisco Meraki. And I am currently interning at NVIDIA doing networking operating systems. I'm also a huge fan of the Rust programming language, as well as, of course, C++. Okay, so here is some table of contents that we will be going over. So we're going to start by talking about what makes a good library and the motivation behind this library. We're going to talk about designing a library for hardware in general. Then I'm going to go into a little bit about how the USB protocol actually works. It's going to be very high level. Then we'll actually talk about my library design, and then we'll have some time at the end for questions. One other thing is this project was done in collaboration with my mentor, Khalil Estelle. He's been mentoring me for about 3 years now. He is a co-designer on this project. Okay, why? Okay, so we had a few motivations for this library. First and foremost, having a modular and flexible system where you can use as much or as little of the library as you want was really, really important to us. We also wanted something that was done in modern C++ for safety and ergonomic reasons. We wanted a system that was hardware agnostic and to not use macros. Constant Spur really helped with that. And we wanted to use exceptions for our error handling mechanism. See the exceptions are code compression talk, the keynote last year. All right, so what makes a good library? This is a really subjective thing. Everyone, you can ask 10 different people and they'll give you 10 different answers. So I can just give you what my belief of it is. Something that is well documented, first and foremost. Like you shouldn't be guessing on what things are. And the abstractions, once you read the documentation, are intuitive and actually make sense. So after you read the documentation, you can understand why a library designer made the specific choices that they did, and that would allow you to basically have higher code velocity and things like that. Okay, so before we can talk about designing a library for USB hardware, we have to back up. We have to talk about designing a library for hardware in general. This is sometimes known as a hardware abstraction layer, or a HAL. It's also the namespace I'll be using in a lot of the code examples. So when we say hardware, designing for hardware, typically we are meaning peripherals on a specific chip or microcontroller, stuff like that. So when you think about hardware in the abstract sense, you can't think about, okay, what properties or what state could this have? You kind of have to only assume, what can this thing reasonably do? In this case, this is an example using an output interface, an output pin interface. The output pin is very simple. It's just a pin that you can connect a wire to that can either be on or it can be off. So what could that reasonably do in software? Well, you can check the level or you can set the level. And as you can see, that's what our interface looks like with the, the abstract base class. You will also see that we have these public methods that are not virtual. That is because this allows us these are just wrappers to call the virtual methods. That is because in case we need to add a specific prologue or an epilogue for a specific interface without breaking anyone else's API. This is an example implementation for one of the chips that we use a lot, the STM32F1. Okay, so why dynamic dispatch? It centralizes the interfaces and creates a uniform definitions. APIs can just use the base class and anything that comes from that specific base class. It's easy to extend, like I was mentioning before, adding prologues, epilogues, whatever. And honestly, the performance and size cost of the vtable is kind of negligible. You can see here, and here's a link to the code that I used for this assembly. It's devirtualizing. It's quite literally just an abstract base class calling a method built on O0. And you can see that it's devirtualizing. And because our interfaces don't have that many APIs to begin with, the virtual table isn't going to have that many entries, and we're not doing that many layers of inheritance. So the vtable in general will be small. Okay, why not concepts? I want to preface this by saying I love concepts. I use them as much as I possibly can. They're lovely. However, we don't believe that they're the right tool for this particular thing, for making interfaces. They're harder to centralize, and they're not as flexible. It's hard to keep track of them. There's no easy way to inject prologues or epilogues without breaking everyone's implementation. I do think that reflection will bring even more power to concepts and actually get to a place where we can emulate Rust traits. A trait is an interface in Rust that can do some fun things. The next thing I want to talk about is data management and ownership. Ownership is the concept of every variable or piece of data is owned by a specific scope. So in this example at the top, you can see that my array is owned by foo. When foo ends, my array will be destructed because foo owns my array. Unowned data is another way to access a piece of data. So a reference, a span, a pointer, a view, anything like that. This is also typically called aliasing, where you have yet another way to access a specific piece of memory. And you can see in the example below that, once again, my array owns, or foo owns my array, and then I'm going to call bar with a span to my array. When bar destructs, my array will not be touched. The span will be destructed, but that's just a pointer and a length. My array will only be destructed when foo destructs. Okay, so this gets into how we handle lifetimes in our code, in our specific library. So what we did originally is we actually had everyone mark their interfaces as static, which means force the lifetime to be existent for the entire program's existence. The reason we did that is because hardware cannot be destructed. Because hardware cannot be destructed, it doesn't really make sense for things representing hardware to be destructed. That doesn't really make sense. So what we did, and the way our library is set up, is every application had their own application entry point. We wrote the int main to make sure that a terminate handler was correctly set and the program counter did not run off and do who knows what, things like that. And then we had this initialized platform that would be per platform, because remember, we want to be hardware agnostic. However, if people forgot to tag this as static, then the thing you initialized would be owned by initialized platform, and when initialized platform ends, you would be left with a dangling pointer, because our application used to take a resource list, which is just a struct of all of the things your application may or may not need. So what we changed to is using PMR smart pointers. Basically, we have a buffer, we have a region where everything is allocated to, and as long as there is a smart pointer in existence, it will not destruct. So this is a really nice way to just not think about it and have everything be automatic, and to quickly pass around different references or pointers to a specific object. Okay, so you saw there that I used strong pointer. This is basically just a lightweight reference counting smart pointer. Shared pointer was just a little too heavy for our needs. Also, shared pointer it can be null, which is not something that we don't want to deal with something that could potentially be null. So strong pointer can never be null. It's just the way it's designed. All right, so scatter span is another pretty important concept throughout our library. Quite literally, at this point in time, it's just a type alias to span of t. And what it allows you to do is just aggregate multiple buffers as a single view. So you can see that I have the teal block, the orange block, and the green block, and they're all separate buffers. But if I wanted to take a look at them as if they were one singular payload, then I would use a scatter span, which would have a view into all of them. In reality, of course, this is just a two-dimensional span, but having this nice abstraction is nice, especially if you need to compose payloads together to be sent off somewhere, which we'll get to in a bit. Okay, let's talk about the actual USB protocol. This is going to be, USB is a very complicated protocol. It has to do kind of everything. It has to be, there are endless number of USB devices. I want to preface this by saying this library and everything in this talk is specifically about USB 2.0. We are considering doing 3.0 and super speed and all of that, but that is a future thing that is out of scope of this talk. Here we go. Okay, if you would like more information on USB, here are some excellent resources that helped me really learn the protocol. I will actually be using some figures from Beyond Logic. They were just super helpful, and this book is very thorough and pretty easily digestible considering the complexity of this topic. Here are some terms that you may or may not know. Just want to make sure everyone's on the same page because I will be referencing these. You have the bus, which represents the actual data lines that have every system connected to each other. You have the host, which is the system driving all communications on the bus. Normally, this is the computer. This is a computer. It doesn't have to be a computer. It's a whole other rabbit hole. Then you have the device, which are typically peripherals. So your mouse, your keyboard, your mic, whatever, that will typically be a USB device. This library is specifically for implementing the USB device side of the protocol. We have endpoints, which is a place to put data to be sent off or received. Think of them as little mailboxes that data gets sorted into for either incoming or outbound mail. And then we have the process of enumeration, which is the process at the very start of the device and host connection where the host is discovering the capabilities of devices on the bus. The next thing I want to talk about is actually how communication works between systems on USB. USB refers to these as transfers. We will only be talking about the control transfer as that is universal to all devices and therefore needed to be accounted for in the library. The other transfers that you see here, those are typically for just data, for functionality data and other types of sending and receiving data after enumeration, after whatever. Control is sort of the way to set up and things like that. So let's actually break down what a control transfer looks like. It's broken down into 3 stages. You have the called transactions. You have the setup transaction, you have the data transaction, you have the status transaction. The setup transaction is when the host makes a request to a device. The data transaction doesn't actually need to exist. There could be requests that require no data to be responded with. And I should also mention with the data, there could also be n number of transactions depending on how big the requested payload is. From the host. The host will tell the device how much data it's looking for, how many bytes. And then the status transaction is to make sure for the recipient of the data to respond by saying, giving a status on how the data was processed. Acknowledged is we got it, all good. NAC or not acknowledged is I'm busy, try again. And stall is I don't understand, typically. So let's talk a little about endpoints. So everything in USB is host-centric. So egress traffic from a device comes out of in endpoints, and that's because it's going into the host. And then ingress traffic for the ingress traffic from the device comes into out endpoints because they are coming out of the host into the device. And again, there are 4 types of endpoints representing the 4 types of transfers that I listed earlier. And once again, we will only be talking about the control endpoint because that is universal across all devices no matter what. All right, so how exactly does the host learn about the device? So like I mentioned, it's the process of enumeration, but what exactly gets sent during the process of enumeration? How does the device describe what it can do? That is specific payloads known as descriptors. And these can range from high-level specs like power or manufacturer information or serial number, or it could be very minute, as in I'm going to communicate with this specific endpoint in this specific way. This is actually the relationship between all devices. So there's a lot going on here, and I should say that these are mostly everything except the green are standard devices that will exist across all devices. So you can see that each one gets a little more narrow. So you have the device descriptor that describes the device as a whole, properties about it. You have the configuration descriptor, which describes specific configurations on how that device is to be used. You have interface descriptors, which represent a specific functionality. So microphone or mouse or keyboard, something like that. Those will typically be listed by the interface descriptor. Then there could be custom descriptors after that. So there could be various, additional data that actually needs to be communicated to the host by the device in relation to whatever functionality. And finally, at the end, you have endpoint descriptors. These basically just say how a specific endpoint is to be used. It's how it's to be addressed, its direction and how much data it can hold, things like that. Here's actually an example of this descriptor. Here's actually an example of what one of these looks like. This is the configuration descriptor. Don't worry too much about this, this is here more for curiosity. Okay, let's actually walk through enumeration. What does this look like? Okay, so on the left, we have the host, represented by that little laptop logo. The box above it is what the host knows. On the right, we have the device, which is represented by that green board. This board is called the HAL board 3. It was made by Khalil and his fiance Milo, who are here today. They did a lovely job on this, and it's what I've been using to do all of my development on. And the box above it is what it knows. So when you plug in the device to the host, it will start listening on address 0. This is the default address, and it says, hello, I'm connected, I'm listening on address 0. The host will acknowledge this and assign it an address. The device will acknowledge. Oh, and by the way, most of these are multiple transfers. For simplification reasons, I'm not going to show every single transaction per transfer because we'd be here forever if I did that. So this is the simplified magic picture version. So the device acknowledges, the host now says, okay, please send me hex 12 bytes of your device descriptor. This is 18 bytes. The device acknowledges and sends it over. Now the host knows a little bit about the device, like the high level stuff. This includes specific strings that may be attached to the device descriptor. Now, I haven't talked about strings yet because they don't cleanly fit into that nice diagram, that nice tree that I showed earlier. Strings in USB are qualified by a specific index that's unique to that string. When that number is put into where that string is a part of. So in this case, you have the manufacturer string and the product string. Those are part of the device descriptor. So those numbers are listed there. As soon as the host learns that a specific string index exists, it may ask for that string, and the device needs to be ready for that. So in this case, it's saying, okay, please send me the first 2 bytes of string descriptor 1 as locale enus. The reason it's asking for the first 2 bytes is because that's the header of the string descriptor, which contains the type of descriptor and also the length of the string. It says, okay, the string is hex C bytes or 12 bytes. And then the host acknowledges that and says, okay, please send me 14 bytes for string descriptor 1 as 2 plus 12 is 14, or hex E. The device acknowledges and sends it over. So now we have our string. The host knows about the company Inc., which is, Now the host says, okay, please send me 9 bytes for configuration descriptor 1. Nope. The device acknowledges it and sends out through the data. Now it knows about the configuration of how this device is to be used. Now you'll see one of the fields there is, oh well. Okay, it's not, the red went away. I don't know. Oh. Uh-oh. There we go. Sorry about that. Okay, so you'll see that the total length field is, there's a field called total length. And you see that I have not actually put a number there. What this field is it's the number of bytes that the configuration and all of its subdescriptors are. How many bytes are all of those descriptors put together, excluding string descriptors, which again are represented by the indexes. So now it's asking, please send me every descriptor associated with this configuration. The device acknowledges it and sends it over. Now it knows the interfaces, endpoints, whatever. Oh, and I should mention another thing. The device descriptor will list how many configurations are present that the device could have. And this configuration fetching process will repeat for however many configurations the device has. A lot of the times, this is only a single configuration. It's pretty rare, actually, for USB devices to have more than one configuration, but it does happen, and we actually support that. Anyway, the device will now, once all the configurations are sent over, the device will now say, or the host will now say, please will now set a configuration. In this case, it's saying, please set a configuration to configuration 1. The device acknowledges it and sets the configuration. At this point in time, the base enumeration is done. Here's a flowchart of the entire process. Yes, it's wild. You'll see that the dashed lines going to host request strings can come from kind of anywhere, as long as it's not in the middle of fetching another descriptor. And you'll see in the purple box the process of fetching string descriptors. You'll also see that this is not the end. There could be specific configuration that could be done after this, depending on your specific configuration or interface. So yeah, it's a rabbit hole. The reason for that is all functionality outside of base USB is its own standard. So if you want to make like a microphone or you want to make like a keyboard, you need to go read the specific subprotocol for that. And so it's a lot. It's a lot to learn, basically. Got all that? No? Okay, don't worry. This is not a protocol talk. I needed to just give some context so my APIs make sense and you can understand kind of how this story took shape. Okay, let's actually talk about library design, the reason that we're all here. Oop. And I just... Okay. All right, so where do you even start, right? That's a lot of information. A good place to start is, okay, what are the components that actually would need to exist in a specific library. What things are common across all devices, no matter what happens? Well, the things that we decided that were common across all devices, the components, as I'm calling them, are the endpoints, some way to manage descriptors, an organizational system for specific USB functions, so USB mic, like if you have a USB mic class or a USB keyboard class, something like that. And then, of course, that process of enumeration. The next question you have to ask is, okay, who actually talks to hardware? How many of these are actually going to need to be interfaced with hardware? And the answer to that question is just the endpoints, which is great because it means that the other three components are fully generic and there is no special implementation that needs to be done per hardware or anything like that. So let's actually talk about these endpoints. Here is the base endpoint class that we have. This is things that every endpoint can do. They can get info. As you can see, here's that little info, the info they can get, which is their direction, their number, how much data they can fit, things like that. They can put themselves into a stall state, which, as I mentioned earlier, means I don't understand, something needs to change. Or they can reset themselves, which differs based on every piece of hardware. Okay, so writing. So these are the in endpoints. Remember, it's all host-centric. Writing is pretty simple. You give it a scatter span, and it will write the payload onto the bus. However, there is a small caveat to this, and that is data is only written onto the bus once there is once the amount of data that can fit within an endpoint is at its maximum. So if an endpoint is 16 bytes, it can hold 16 bytes, it will not send off until you send 16 bytes. Or you flush by sending a zero-length packet, which is a data transaction with no actual data. The reason for this is the way USB data transactions work in general is the host will assume the transaction has ended if it receives a packet that is smaller than the maximum. So if you want to send 32 bytes, 16 bytes, 16 bytes, zero-length packet. If you want to send, 17 bytes, 16 bytes, 1 byte, the host goes, okay, I only received 1 byte and not 16 bytes. This transaction's over. They must be done sending data. Now, another thing that I touched on very briefly, but I just want to bring up again, is the host will actually request how many bytes it's expecting and how many bytes it would like to receive. If the device does not send the correct amount of bytes, the host will respond with a stall, saying it doesn't understand what you're doing and stop talking to you. So it's really important that everyone is speaking the same language and things like that. So just some extra protocols stuff that could be interesting. Okay, reading. Reading is a little more complicated because reading is interrupt-based, and for those who may not know, an interrupt is just a signal to the CPU where the CPU has to go do something. Think of it like a notification where you need, like a very urgent notification where you need to drop everything and go deal with the notification. The way this works typically is there is a interrupt service request handler. And what that is it's a specific function that the CPU will jump to when a specific interrupt is raised, or triggered, I should say. That on receive function that you can see that takes a callback, that callback will be the function that is called on a specific interrupt. And then, of course, read is read. Here's the data, do what you want with it. Here are the actual endpoint APIs. So all of these, the reason we have all of them separate, as you probably noticed, in and out look very similar except for a couple of functions. The reason it's like this is to make sure that you are actually giving a specific interface the thing that it expects. So for example, if you have something that can only write. You want to make sure you're only giving it something that can write and not something that may also read or can only read for some reason. So that's why it's differentiated like that. It's just extra type safety to catch errors early at compile time. Okay, you'll probably see this is the one endpoint I haven't talked about yet that it wasn't listed, and that's the control endpoint. And that's because it's special. It's the only bidirectional endpoint. It has a few additional responsibilities, and that is connecting the entire device to the bus and assigning the device address. It has those abilities because it is heavily involved with setup and typically will be the one needing to facilitate these types of things anyway. This control endpoint is not to be used by interfaces or APIs directly. Or drivers, I should say. It's kind of exclusively to be used by the enumerator, so the enumerator can perform setup. Technically, that's it. That's all you need. You can handcraft everything, descriptors, and walk through that crazy flowchart that I showed earlier. Everything in USB is little endian. That's what LE is. And it'll work. We have a demo for it on our GitHub. However, that's a lot of moving parts for a single peripheral. It would be nice to have a system for that, right? Just to have it automatically work. Okay. But before that, we need to take a small detour, and we need to talk about the concept of inversion of control. This is a software design technique. Imagine, typically it allows a caller to give a callee temporary access to one of its resources. So imagine that we have some resource R that can write a scatter span to a piece of hardware, and say we have these two functions, caller and callee. Now, if we don't want to give callee direct access to the resource, there could be any number of reasons for that. It can do other things that we don't want callee to accidentally invoke, or maybe there are other use cases for it, things like that. We just want to give temporary access to the ability to write. So what we can actually do is we can allow callee to take a lambda that takes a parameter of the scatter span that it would like to write, and then the function that we actually pass it. Sorry, I meant to say take a function, and then now I'm talking about lambdas. Sorry. Then we create a lambda that captures R and writes out the buffer that's passed in via the parameter. And then to callee, we just give it that function. Callee will do whatever it wants, construct its payload, and then when it chooses, it will choose to write out the payload that it's constructed. And we don't have to give it access directly to R, but it can still access R, write to R by using our callback. The other thing I want to talk about is managing descriptors. This is pretty important because it's actually how, like I said earlier, communication knowledge is passed. Most descriptors are ephemeral, that we found out, which means that they're only needed at their specific phase of enumeration. And a lot of descriptors, if you don't already know the type of system you're building, you can't, at compile time or at writing time, you can't assume what specific fields may be. A good example of that is total length. Total length, like I mentioned before, is the number of bytes that a configuration and all of its subdescriptors are. If you are building a generic system, you don't know that length. So all of that has to be calculated at enumeration time. The same goes for the indexes. You don't know what the indexes are going to be until you actually go and enumerate. Okay, let's finally put everything together into one nice interface. So I know there's a lot going on here, but it's not actually that complicated, I swear. Okay, so we have This is the class that all specific interfaces will inherit from. So your microphone, your keyboard, things like that. One thing I should mention that I think I forgot to mention earlier is we have decided to make our collection management function, the organization management function, structure, at the interface level, which basically is just anything below configuration, because that's typically where in the USB standard you are supposed to dictate specific functionality. So in this particular case, because we're building a generic system, we expect the interfaces themselves to manage their own descriptors. Interface descriptors, custom descriptors, endpoint descriptors. We also expect them to manage their own resources, whatever endpoints they may need, anything like that, any additional functionality, that is up to them. And we'll get into these couple of functions in a minute, but I just want to touch on handling requests. So requests, as I mentioned prior, you actually, the device can receive requests, but interfaces and endpoints can also receive requests. Because of that, interfaces need a way to handle that, because obviously the generic library will not know what your specific interface can and cannot do. So we have a system for that, and you'll see that it takes a callback like everything else in here. And here are the two structures that will become important in a second. Okay, let's talk about this function first, write descriptor. So this function has two jobs: populate indexes for interfaces and strings, and it also has the job of aggregating all of its descriptors together and sending it out via the p callback. Now you'll probably notice that I set these are optional. This is the struct that it takes in, and what these are is it's either it'll be the first number that they are to start counting from. So for example, if 1 is given to both of the fields, the interface knows, okay, I can start at index 1 and use as many as I need. And then it will return however many indexes it has used. So if there's 3 strings, it'll return 3 for string. If there's 4 interfaces, it will return 4 for interface. Things like that. However, the reason they're optional is because this function, write descriptor, could be called multiple times. We'll get into what that looks like in a sec. But you may not want to update, on subsequent calls of this function, you may not want to update those indexes because you may already have a system in place and it gets confusing to fix things or whatever. So because of that, yeah, that's why they're optional. Okay, write string descriptor is a little more straightforward. All this does is you have some logic to find your specific string, and if it's found, given an index, and if it's found, write it out and return true. If it's not found, do nothing, return false. The reason it's like this, instead of having like throwing an exception or something like that, is because the way the enumerator and other things may use this function, is it may have to iterate through all possible interfaces or configurations. There are ideas on how to make that a little more efficient, but you typically don't have that many things to iterate through, so it kind of doesn't matter. But that is the reason why it just returns true or false and doesn't throw an exception or anything like that. Here's an example implementation. So we have some CDCs. Yeah, so we have some CDC fans in the chat. For those who don't know, CDC, or communication device class, it's a virtual COM if you're on Windows, or serial port if you're on Unix, where the device will stream data to the computer. Here's a bunch of things that may or may not be, that would be needed. So, here's things to facilitate data. Here's a thing to facilitate status. Here's constructing everything. Here's their interfaces, stuff like that. Or your descriptors. Yeah. Okay. But the one part of descriptor management I haven't talked about is device and configuration descriptors. The reason I haven't talked about these is because these are actually managed by the library. And the reason they're managed by the library is because, well, no specific interface needs to care about this, or they need to care about it, but they don't influence its configuration. So the device descriptor, we basically just provide utils for all of this stuff. You don't have to use these. They make your life easier if you do, but they're kind of optional things. The device structure, for example, is it's just a wrapper on an array to make sure you are accessing the correct areas of where the fields are. You can see that down here. It's a packed array. It says 16 bytes instead of 18 because the headers are calculated on the fly during enumeration. Yeah. So I didn't talk about configuration yet, and now I'm going to do that. And this slide has a small, graphical error on it. Pretend that X isn't there. Okay, so remember that a configuration can have multiple interfaces, right? Okay, so the configuration needs to know about those interfaces, at least in some capacity. So how would you do that? I'm going, how, this is me trying to figure this out. So one way, and the way I originally tried doing it, was just have an array, have your template parameter n of size t and make an array of interfaces. Okay, that seems reasonable. We have a problem though. Remember that the device can have multiple configurations, and those configurations can have multiple interfaces, and they can all be different number of interfaces as well. So if I want to construct an array of configurations, what goes here? So that's what the X is for. You can pretend the X is real now. So what type is this sort of thing? That doesn't work, sort of thing, unfortunately. But we have a solution. And the solution is to check your animation edits before editing them at the end of the night. Okay, anyway, the solution is to use PMR vector. The reason we use PMR vector is because this will actually keep the configuration type the same. So you can have an array of configurations now. And so I'll walk through kind of how this works. You have a concept basically constraining the type of variadic arguments that can be passed here. It has to be derived from the interface base class. And then of course we have our variadic arguments. You pass in your other information, and then you pass in a strong pointer to each interface. Remember, we manage everything using reference counting. And then, well, that's great. We all know all of this at compile time. We can reserve how much data we need. This is a constant expression since C++ 2820. And then to actually add all of the interfaces from the pack into our vector, we fold over the comma. And yeah, now you can see, so here's the enumeration design, and you can actually see I have my array of configurations, and it works. They're all the same type. Okay, the enumerator design definitely was the hardest part for me. A lot of sleepless nights, a lot of redesigns, a lot of, tear it apart and rebuild it sort of thing. There's a lot going on here. So what we eventually did is I split everything into two phases. We have realization and we have writing. Realization, I alluded to earlier on how a lot of descriptors need to be calculated at enumeration time if you don't know the pre-existing schema ahead of time. Realization is that process. Writing is self-explanatory. Okay, so a lot going on here. We're going to walk through it step by step to make sure what's going on here. So this snippet is after device the device configuration, the device indexes and configuration indexes for strings are set. And because of that, now we have to look at the interfaces. The reason I've cut that out is because it's pretty self-explanatory. You can imagine what the code would be. But for the interfaces, it's a little more involved. So you can see we're going to iterate over every configuration. We're going to say, okay, we need to calculate total length as well. Okay, so let's calculate total length. We know that total length is going to start with 9. That's what this constant resolves to, because that's how large a string or a configuration descriptor is. Then we're going to iterate over all of the interfaces that configuration has. And we're going to then call write descriptor. But instead of giving it the control endpoint, we're just going to give it total length. And we're just going to say, instead of writing out the data that you are passing this function, just give me the size of it and add it to total length. This is what I mean by this function will be called multiple times. This is the first time it's being called. The indexes are being assigned, and instead of writing out the descriptors, it is just calculating their length for that entire configuration. Then at the end, we update I forgot to mention that we are tracking how many interface indexes and how many string indexes we have. I should have probably put those up here, but oh well. So remember the write descriptor function returns back how many interfaces and how many indexes for interfaces and strings it's used. And we simply just add those to our count for the next go around, for the next interface in this configuration. When we're all done, we assign the number of interfaces by the number we calculated. And then we assign the total length by the number we calculated. So yeah, that's realization. Not so scary now. Here's the scary part. Writing descriptors is, I'm simplifying very heavily here. And again, we're going to walk through this slowly. I know there's a lot of code on screen. So after realization, we need actually a way to wait for data. Because remember, it's interrupt based. We have to get notified that data has arrived. And by the way, when senders and receivers come out, this will make this whole process very easy, much more nice. We plan to do some work with coroutines to make things a little more asynchronous and not I/O bound. Anyway, we set this callback to be notified when data has arrived on the control endpoint. We connect to the bus, and then we enter our main loop. We wait until data has appeared. When data has appeared, this variable is set to false, and we break out of this loop. Then we set it to true for the next go-around. Then we actually parse out the request packet. The schema of the packet is not super important. All you really need to know is that it contains a type of request, a few extra parameters, including the recipient, and it contains how many bytes have been requested by the host. So we make sure that the recipient is the device, because it doesn't make sense to have a recipient that's not the device at this point. And then we go and handle the device request. The reason I'm not showing this function is because it's this. This is the function. So it's switch cases on top of switch cases, because remember, there are different types of getting descriptor. So yeah. Then we do this over and over again until a configuration is set. Then once the configuration is set, we know that enumeration has finished. But before we exit our main loop, we actually set a new flag called hasSetupPacket. And the reason for that is, I'm not showing it here, but I have another function that is listening for interrupts listening for interrupts on the control endpoint for further setup packets, which could either be further device configuration setup or could be interface specific or endpoint specific setup. And here's my lovely flowchart. And that's basically it. That's the library. Any questions? By the way, this QR code is to my LinkedIn. Connect with me.
Thank you. I learned new stuff today. That's nice. I'm concerned about your application main. Do you claim the main loop, or can we use it for only event loop afterwards, initializing the USB stack?
The main application loop. So that is outside of the USB component to this. That is just the entry point for the specific library. That can be used however you want. You can have a super loop, set up a scheduler, whatever you want.
So just to be clear,
yeah.
I can initialize the stack to my CDC ACM because that's what I want.
Yeah.
And then I can go on with my normal application loop afterwards, and then it will
just work?
Just work.
Correct.
Excellent. Thank you very much.
Of course, yeah.
Hello. So I have, hopefully there's time for 2 questions.
Yeah, no, go for it. We have plenty of time. I finished exactly on 50 minutes. I am proud of myself.
Awesome. So the first one is in that last slide you were showing with the loop. I saw that busy wait while waiting for data immediately makes me think, could this be made asynchronous with coroutines or something? Is that in the works?
It is in the works.
Okay,
yeah.
Awesome.
So I alluded to that earlier, and I guess I'll reiterate because I didn't really have a place to come up naturally. We are working on making this entire library coroutine first. So the whole thing, because a lot of embedded systems is actually I/O bound, coroutines are perfect here. Mm-hmm. And you don't pay for extra, it's just a different way of organizing your data, organizing your logic. So yeah, coroutines are in the way. Khalil has worked very hard on that. C++ gives you a lot of control with coroutines and kind of says, go forth. So yes,
awesome.
They're in the works.
My second question was, you were speaking at the beginning about how hardware needs to live for the duration of the program. Users are unpredictable. Sometimes people just unplug devices. Is that handled by that, or how do you handle if you're assuming the hardware exists for the entire duration of the program, how do you handle a user just unplugging the device?
So when I say hardware cannot be destructed, I'm not talking about the actual connection to the host. I'm talking about the internal hardware that manages USB.
Oh, okay. So
the USB the device controller, and the endpoints, those they're not going to open the device and rip out the chips.
Yeah. Okay. If they do that, that's their own fault.
If they do that, we do not support that.
Right, thanks for interesting and insightful talk.
Yeah.
I want to pick on something with the strings and interfaces indices. So do I get it right that there is a global list of all these strings that the device can return?
So at the current time, no. I want to personally work on that. So currently the way we fetch specific indexed things is iteration. I want to change that to a hash map. Just so you have a lookup table for everything, and then you would be able to easily request everything. It can be done with iteration. You know the maximum value of indexes that exist. You can just make a thing for that sort of thing. But
the host, when it wants to learn the value of a particular string, it will tell the device, hey, tell me the string number 10, for instance, right?
Yes.
So from this perspective, there's a list of strings predefined that the host is able to request. I mean, up to maybe 20, right? The first one being the manufacturer, the second one that you show the
product, yeah.
So maybe the interface number 4 will start at offset maybe 21.
Yeah,
it's so right?
That's up to the user on how that's up to the app developer on how they want to do all that. The library is designed in a way where you can set the starting index to whatever you want. You can set the incremental system to however you want. The only thing it assumes is the later things being enumerated have higher index values.
Got it. So it doesn't need to necessarily start at 1.
No, yeah, it doesn't have to start at 1. I personally started at 1 because the maximum you can have is it's up to 255. So
not that many though.
Yeah.
Okay, fair enough. Thank you.
Yeah, of course. Yeah. Thank you.
Thanks for the talk. I've got a couple of questions.
Of course.
So piggybacking on that hardware question from earlier, so whilst the hardware inside the chip can't be like unplugged, as in just as easily, a lot of hardware devices have this concept of like clocking on and off peripherals to kind of like save power. So if you're not actually using something, you turn it off so it uses less like power. Is that like a consideration you've had to maybe like if something has been turned off, then no pointer to it can exist, and when it's turned on, then the pointer can then come to existence, that sort of thing?
So I've never had a use case for that. I believe that I think we might support a little bit of that. Of you can turn. We have low-level functions in the library that manage power, so you can turn things off, turn things on. It's typically platform-specific. I personally haven't done anything with that, so. But yeah, I mean, that's like a completely valid use case and completely like good thing to have. So absolutely, thank you.
Yeah, fair. The second question is about the out endpoint interface. So it has the on receive that takes the callback to let you know that packets come in. And then there's the read method as well.
Yes.
That takes a span. I wanted to know, so if it takes a span, this means that upfront you have to allocate, create like an array or vector with the memory and then call this method with that to have it populated. How do you know what size to pass in to the interface? I saw it returns a size, like how much it wrote.
So I've made a helper function called getScatterSpanSize, which will do basically that. I might be able to. Oh, it might be. Yeah. So if you look here, ScatterSpanSize, that will get the individual elements of how many that is. That can tell you how much to allocate. The thing is, at compile time, you don't know this, so you allocate an upper bound. Or you don't allocate at all and you just use the view directly. Sometimes you don't, if you only copy out unless you absolutely have to. Yeah, that's kind of the idea, yeah.
Okay, cool.
Yeah.
My last question, I promise.
Go ahead. Yeah, no, we're good on time.
So the interface struct, the one that's implemented by the CDC interface, I think. I was wondering if, well, I guess first of all, does the library support alternative interfaces?
It does.
It does.
So interface association, CDC uses that actually. So yeah, it's anything below, that's why I said anything below configuration.
Oh, okay, good. That makes sense. Thank you.
Of course, yeah.
So I haven't yet worked with USB, and I'm looking forward to trying this out.
Yeah.
On your next slide, you showed that there was a callback for when you're reading and you're connecting, you're just waiting for data.
Yes.
You also said that reading is interrupt-based. So I'm wondering, what's the risk that while you're processing this data, you might receive another packet, get interrupted, and the data that you're trying to process is being overwritten?
So the protocol should disallow this. If you get a new interrupt, the idea is that devices and hosts, you always assume the latest data is accurate. If you have two interrupts back to back, typically someone's not playing the game correctly. And the reason I say that, if we jump back to, actually I think it's probably faster if I just do this. I want to jump back to just the transaction slide. Here we go. So you'll see actually after inside each transaction, you have different phases. Yes, there's a lot of nesting. That contains an acknowledge or some sort of handshake back and forth. There's also a CRC that needs to be validated. If it's not validated, I believe a NAC is issued. But if you shouldn't be receiving multiple, you shouldn't be receiving a stream of data. There is an exception to that. That is the isochronous data transfer, which is for streaming data. Although that does still have specific rules that are out of scope. But you should be receiving some sort of handshake before more data has, or you should be issuing some sort of handshake. So if the host is requesting data. You will send the data, it will acknowledge. You will send the data, it'll acknowledge. You'll send the data, things like that. Yeah.
Okay. So coming from a background with hacking and cheating in video games, doing things that the hardware wouldn't expect, that sounds like that can be abused.
Absolutely. Yeah. So what it would do, so what should happen is you assume the latest interrupt is correct. So yeah, you assume the latest interrupt is correct. So if another one comes through, you're reading the buffer anyway. If you read too early, then you have use for, corruption could occur. But there are methods of dealing with that. Again, CRCs and other things like that. I didn't show any of that because most of that happens in hardware.
Right.
But yeah, the hardware does a lot of heavy lifting actually for this protocol. So, and I didn't there are many more steps of enumeration I didn't talk about because they're hardware based. Right. But yeah, no, that's an interesting idea to actually test that and see what happens. Because now I'm curious. It's just not something I've tested. But thank you. Yeah.
Thank you.
I actually want to clarify that. In the USB specification, once the host sends a message to the endpoint, it gets nacked. So there will never be another message. You won't get another interrupt until you have read all the data out and then said that endpoint is now valid. That allows the host to actually send you another message. So once you got the interrupt, you can just read the data whenever you like.
Sorry, I'm newish to this protocol still. Thank you very much. Yeah. Thank you. Yeah, so thank you so much for coming, and huge shout out to Khalil once again as a co-designer and educating me on USB and things like that. He has read way too many books on this and has made it so I don't have to read as many books. Thank you. I'll be around for questions if anyone wants to talk to me.